Welcome everyone to today's TEWI-Kolloquium, which is a series of talks that we are hosting here at the University of Klagenfurt in Austria, together with this non-profit organization that is called Förderverein Technische Fakultät, which tries to connect research of academia with industry. And in this case, we invite always experts to present new topics, new ideas, novel approaches, and like today, also a new standard. And I'm very happy and I'm honored to welcome and introduce Werner. He is a key researcher at Digital, the Institute for Information and Communication Technologies at JOANNEUM Research in Graz. He received a degree in media technology and design in 2002 for his diploma thesis on motion estimation and segmentation for film video standards conversion. And his research interests include audiovisual content analysis, multimedia retrieval, and machine learning. And he regularly contributes to standardization, among others, in MPEG, where he co-chairs the ad hoc group and also the breakout group on neural network compression. And this also brings him here because he is chairing all this activity that led to the standardization of compressed representation of neural network. But now the floor is yours. Werner, please go ahead.
Thank you very much, Christian, for the kind introduction, and thank you for inviting me to this talk. And yeah, unfortunately, we still do this kind of things online. Would be nice to be in Klagenfurt today. So yeah, this is part of the work I'm doing in MPEG. As some of you are also pretty much involved, but probably more on video coding and streaming sites, and this is one of the other of the many things that go on in MPEG that come more out of the tradition of description coding, and then at some point realizing everything that is around video description nowadays also uses neural networks, and those are also large, and we have compression expertise in MPEG, so why not put these things together? And of course, nowadays also the compression itself started moving towards neural networks, so maybe we also start then sending networks for inference of a codec around in a compressed way. So in today's talk, I would like to give you a bit of a context of why we have been starting this work, talk a bit about the state of the art in neural network compression, as has been a quite active research topic in recent years. Then talk about the standard. So why do we need one, and what are the design considerations behind? Then talk about the coding methods we have in the standard and the high-level syntax, and then give you a bit of information about the performance we achieve. And also talk a bit about the ongoing work, because this is, as always, just the first step, but there's still a lot of things to do ahead. So, as you all know, artificial neural networks have been widely adopted. Of course, in MPEG, this is very much motivated by applications in multimedia. So a lot of visual audio content recognition classification tasks nowadays rely on neural networks, speech and natural language processing tasks as well. And even if you think of speech models, they tend to be even larger than many of the models we use in computer vision, for example. So we have large networks, and networks have been growing over the last decade when deep learning has been taking off. And we have lots of parameters, weights, but also other terms, biases that form that network. So we have a large amount of data to handle. So in training, we learn those parameters from data, and typically we do that once on a powerful infrastructure, although also this is moving towards more distributed and federated settings. And then updates and adaptations in the target environment may be necessary, so doing some fine-tuning maybe. And inference uses that trained network, and there's basically two main things that may happen where compression could make sense. you need the network with all the parameters, so you need to send that large amount of data somewhere. So I think you need to deploy networks to mobile devices, as mobile devices get equipped with specific processors where network inference also becomes effective. This is more and more a use case. Also, smart cameras are something that gets increasingly deployed, and you might have a network of smart cameras. So you potentially deploy that network to thousands, 10,000s of devices. So the focus here is the size to be transmitted. You want to make sure that you send the network or an update of it with as little data as possible. The other thing is that many of these devices are also resource constrained. So it's mobile phones, it's smart cameras, but it's also with 5G. A lot of the advances in 5G come by doing more things on the edge and having more intelligent nodes across your network. But they are also very resource constrained. So there, the low memory and computational complexity during inference is actually the key. Of course, you need to have gotten the network there once, but the most important thing is there to save energy. Now, in some cases, those two goals may fit well together and could be served by the same technology. In some cases, they may be more difficult to harmonize or even be contradicting. So, looking at the state of the art in neural network compression, a typical pipeline consists of 3 steps. The first one is reduction of parameters. So you try to remove something from your network that doesn't contribute much to the result. This can be eliminating neurons, which is typically referred to as pruning. So you reduce things that are larger structures, possibly even entire layers, maybe in some cases, some channels, depending on your network. The other thing is you reduce the entropy of a tensor. So you keep everything you have, but you maybe make your tensor better compressible or sparser, or you decompose and transform a tensor. So this is like a fairly traditional approach, but still it is quite useful here, trying to replace higher dimensional tensor by product of lower dimensional ones, giving a good approximation and reducing the computational effort. So at the very well-known IAClear paper from Han in 2016, this was actually the first paper that rolled out such a complete compression pipeline with some specific technologies at each of these steps. But this is one of the works that kicked off a lot of follow-up research and then working on some of these steps. So then the second one is reducing the precision of parameters, so quantization. That's fairly widely applied already, although very often in a rather simple manner. And there's also work that shows if you try to do that more locally and more adaptive, the gain is larger. And finally, performing some entropy coding, like in traditional compression, which is the step that you need to undo to use your network. So for pruning and sparsification, there is a large number of methods, and it's very often rather simple to implement. So in the simplest case, you just look for weights with a small absolute value, and you eliminate those parts of the network. It strongly depends on the initial model. I will show those diagrams that you see on the right and on full screen in a moment. And at low compression rates, you even get sometimes performance improvements. So making the model sparser sometimes even boosts performance. And the other thing is that the performance loss, if it appears, can be regained by training. So you do some fine tuning on the sparser structure, and you regain the loss that you have because you can adjust the weights to work well on this structure. However, the computational effort is a concern because you need to assess the performance after different decisions you have been doing. And especially if you need to do training again, this can be a quite costly process. So here's from a recent survey paper, an overview of quite a large number of methods. And basically every column that you see here is one network. So VGG16 is on the very left, and if you look at the scale, you see that 0 is roughly in the middle in most of the plots, which means that at moderate compression rates, you always get a boost in performance. And VGG is a very verbose model, so to say, where this works. But then if you look further to the right, so for example, resonant 50 in the third column, you see that the 0 line is nearly at the top of the plot. So improving performance is not or hardly possible anymore. And then you see that you get a performance drop rather quickly, and something that's not here, but more initially sparse models like MobileNet. You see that this is even harder, and it's much harder there to get a significant compression ratio without sacrificing performance. One interesting theoretical result was published in iClear 18, the so-called lottery ticket hypothesis. So the idea is for a dense randomly initialized feed-forward network, there are subnetworks that achieve the same performance at a similar training cost. And so the lottery ticket is to find the right subnetwork. It's a theoretically nice result, but of course, practically, it's not always easy to find the right subnetwork.
Werners Audio ist bei mir jetzt ausgefallen. Ist das jetzt nur bei mir?
Ich höre ihn auch nicht mehr.
Yeah, it seems audio is.
So can you hear me again now?
Yes.
Okay. No, what my headset decided to do. So I don't know, but until when did you hear me? Just start again with that slide.
Yes.
Okay. Yeah. So lottery ticket hypothesis was something that was published in iClear 18, and postulates that for a dense randomly initialized feed-forward network, that there are subnetworks that achieve the same performance at a similar training cost as the original network. And it's a theoretically nice result, but finding that subnetwork is of course not trivial. And in the meantime, it has also been shown that such a subnetwork could also be obtained by pruning without applying further training. So this is actually good news, because that's a computationally more efficient way of finding the sparser network. And another approach that is used is to retrain from an early training iteration to choose from a few training cycles which subnetwork looks like it could fulfill that properties, and then just retrain that one. One nice thing about pruning and sparsification is also that in many cases you get also an inference complexity gain. It makes not only your network smaller, but it's also more efficient to run inference. So for pruning layers and channels, this is of course very straightforward, because there is less structures you have to process. If you do sparsification on a tensor, that's a bit more tricky, because it needs support on the target platform to actually make use of the sparse tensor. So for example, CUDA has recently added support for that on the recent GPU architectures. And it usually needs to meet a certain sparseness ratio before that gain actually materializes. And so maybe in some cases it's better to stick with the full matrix. So for quantization, as I said, that's widely applied already, and it's possible to go below 10 bits, maybe 8-bit, 4-bit for many networks without sacrificing performance. Again, running fine-tuning or already training with a network with quantized weights will regain the performance loss. This is especially true the further down you get. So for 1 bit, so binarization is very important to run the fine-tuning step, and also there's specific precautions that need to be taken because you get into problems of not running the backpropagation algorithm anymore because of not differentiable functions, vanishing gradients, and all these problems. So there's a number of works that try to address this for the very low precision cases. And also mixed precision, for which also hardware support has increasingly been available now, is beneficial. So you mix per layer or even on a finer granularity the precision that you're using, and don't use the same for the entire networks. So again, for making use of the inference complexity gain, you need support on the target platform and also in the deep learning framework, which is especially tricky in some networks that use some custom operators because they would also need to support that, and you might to add an implementation for that. And it's increasingly supported on GPUs and of course in particular on the specific neural network cores. Compression has some relation to network architecture search. You could say it's just finding an alternative architecture and then train. But network architecture search is actually a very, very costly thing. So I've put in this table, which is for a neural architecture search case where you have the energy comparison is actually a very, very widely cited paper also in the media that compares like how many years you could use your car compared to running one architecture search cycle. But there has also been work now for faster neural architecture search methods that try to avoid basically this trial and error training and then searching in that space. And once you have found such an architecture, then you can use knowledge distillation or similar methods to transfer from your full model. Of course, the other drawback is that for architecture search, you typically need access to the full training data, while if you just do the fine-tuning, like for the other steps, it can be done with just a small share of the data or even application-specific data, not requiring the original training data as long as the distributions are similar enough. And of course, there's the question for the relation to target hardware. So in some cases, you would want to optimize for target hardware because there's supported operations like sparse matrix multiplications, the precisions that are supported, and also the relative costs you have on a particular platform, memory access, certain computation operations, that those trade-offs may be very different on different platforms. And so one idea is to train a network and then derive a network from a particular platform. There's first approaches here, like this once for all from iClear 2020. But the problem is still that there is no reliable prediction of the inference costs on a particular target architecture. This is still a fairly complex problem. You don't have a simulator that very easily gives you the number for a particular network. And in particular, if you want to, for memory, it's a bit easier, but if you want to predict speed and especially energy consumption, this is very, very tricky. And you also see that in the deep learning frameworks. If this was easy, they would use that. But basically what they do is run this auto-tune where they basically try operators and then based on the measurement data decide what to do. So also this is something that would very much benefit from a better prediction of those properties. So now the question is, where do we need a standard for that? So we start from a trained network and we have one interface where we go from that network to an accelerator library. Here it's important to have a standardized format, and compression is useful in some cases. And then we go from that optimized network to inference on a particular platform. Compression is crucial there, but you get more into this hardware dependencies. So the first one is something that is covered by formats like NF and ONNX in exchange formats, but they have only very basic support for quantization. And also what has come in now is accelerated libraries supporting multiple backends like Intel's One API that tries to have an interface here. So what does this mean for the work we did in MPEG? So the idea was to develop a interoperable compressed representation, and of course build on the know-how that MPEG has on compression from various types of both multimedia data, but also others. You know, there's genomic information compression and other work to enable multimedia applications to benefit from the progress in deep learning and cover a broad set of relevant use cases. Of course, all the traditional classification use cases, but also content matching, where you may have descriptors that come from deep neural network, but also content coding. And those have been used for validation. So it was clear that we wouldn't want to define another exchange format because there is some around. There is NF, which is a fairly nice chrono specification, although not too widely adopted. And there is ONNX, which is a less nice specification, but more widely adopted. And of course, there's the formats of the common deep learning frameworks. So those specify approaches for representing the topology, so there's no need to redo that. With a very dynamic environment in terms of inference hardware, it was also clear that we wouldn't want to get too close to a particular inference platform, but be agnostic to the specificities of such a platform, and then maybe have a second step that is on a particular implementation that then applies an additional acceleration. And this is maybe something that an out-of-the-box accelerator library might do. And then there's also the case that different types of networks or applications are best served by different types of compression tools. So there's definitely not one compression pipeline that would serve ideally all the use cases. So for evaluating the compression technologies, the obvious thing we're interested in is the compression ratio, of course. And then the next thing you would think of is, okay, you look at how you reconstruct the original network. So you could compare that like calculating the PSNR for multimedia data, which also there gives you some information, but maybe not everything. And actually turns out for this case, it's really not a useful metric, because if as we have seen with quantization and pruning, you can drop a lot of information from your network and still achieve similar performance. So reconstruction of the original parameters is actually pointless. So this means that the only way to properly evaluate the quality of your reconstructed network is to measure the performance in a target application. So for example, image classification. And it needs to be assessed with the metrics you have there. So you could compare that with the perceptual quality metrics for multimedia. So you're not interested to reconstruct every pixel, but if the user doesn't see a difference, that's fine. And this is a similar case, which of course means it requires models and data sets for each target application, and you cannot test on an unlimited number of applications, which and you cannot generally make an assessment, but you can make it for that set of applications. And then, of course, runtime memory consumption of the encoding and decoding process itself, but also of inference of the resulting model, because that's, for some use cases, a very important thing if the compression also enables more efficient and memory-saving inference on the target platform. So this is the pipeline we set up. We start from an original model, we compress it, decompress it, have a reconstructed model, and run inference with it. So we have the model sizes of the original size. We have the compressed model size as it's stored or transmitted. Here, one issue is that you need to consider the format, because just saving it in another format may impact the size quite a bit. Then we decompress it, and we have a memory footprint of the model as it's ready for inference. That's a more straightforward metric to compare. Although this may also be different for different target platforms. So if you have something that can work within lower precision representation, of course, your memory footprint becomes smaller. And then we are measuring the performance of that network and compare it to the performance of the original model that we sent into the compression pipeline. And we measure that performance with and without fine-tuning, because there may be applications where you can't afford fine-tuning computationally wise, or because you don't have access to the data. So as I said before, there's no pipeline that fits all. So this led to having the standard as a kind of toolbox where you have those different steps, mainly these 3 classes of steps that I mentioned before. And then you have different tools for each of them. So it was a number of parameter reduction methods. I'll talk a bit more in detail about those. There's a number of quantization methods, and there is an entropy coder. And we get the bit stream, and then the pipeline goes back, maybe all the way or maybe not. So at this point in the encoding pipeline, we can theoretically represent the model still with any model representation. For a sparsified or pruned model, that's more straightforward. Although if you have something like decomposed or sparse matrices, the representation that you have in a standard format may not be efficient, and the same is after quantization. Maybe you could still represent it in a standard format, but maybe the representation is not efficient. So that's why there is the additional entropy coding step and going to a specific bit stream format to basically make use of all the gain we could get to achieve a small stored or on the wire representation of the model. Now on the way, so the model, that's what we actually store or transmit. And on the way back, we could actually, after just doing the entropy decoding step, the model could be used depending on where we want to use it. What we get back now is a quantized model. So if we have a platform that can work with the quantized representation we have, the model would already be usable. If the model cannot work with the quantization we're using, or maybe it supports 8-bit and some of our layers have 4-bit, so we do a reconstruction, or at least a partial reconstruction, and then again, model could be usable. For example, if we have something like sparse matrix representations, then it might require reconstructing the entire tensor to make it usable, or it's supported on the platform. So in the end, also the parameter reduction step is partly redone. Of course, things that have been pruned entirely are not reconstructed, but for example, decomposed matrices may be reassembled, or sparse matrices may be reconstructed. So now, getting a bit into details of the methods that are in there. For sparsification, we have a general sparsification method that performs fine-tuning and determines sparsity loss. That is basically on the magnitude of the weights, and then the overall loss in the model is replaced with a weighted sum of the task-specific loss and the sparsity loss. So you can trade off how much you want to optimize for your original target or for sparsity, and then all weights below a threshold are set to 0. So that's fairly straightforward. Another way of sparsification is microstructured pruning. It makes use of the general matrix multiplication algorithm that is at the core of many deep learning frameworks and also hardware implementations. And what happens there is that if you have larger matrices, they get tiled. And so here the idea is that you reshape your tensor into a block structure, either 1D, 2D, or 3D, that matches the tiles that you would process internally in your matrix multiplication algorithm. And then you set entire of these blocks to 0. And you keep a mask that tells you which blocks have been set to 0. So this means you can skip multiplication of entire blocks. Pruning is used in combination with one of the sparsification methods. It starts with performing a weight importance estimation. So it uses graph diffusion on output channels to get a weight redundancy metric, and proceeds iteratively to determine that importance weight, prune neurons according to a set target ratio, then optionally apply one of the sparsification methods, and then repeat this until the target is actually reached, because it's always not easy to exactly predict where removing something will in the end put you. Then there's two more reduction methods. One is low rank decomposition. So that's fairly straightforward. Decompose a weight matrix using singular value decomposition. And you have two lower rank components. You can choose the rank to trade off the reconstruction error versus the number of parameters you get in your final model. And your matrix is basically approximated as the product of those two smaller matrices. And the nice thing is also you can modify your model to just have those two tensors and their multiplication in your pipeline, so you don't need a specific means to represent that. And then there is something we call unification, which is a generalization of the microstructured sparsification method I've described before. So again, with the idea of working with these blocks that you use internally in the matrix multiplication. But instead of setting them 0, the idea is here to approximate them just with one value, keeping the sign of the value. And again, keep a mask of those blocks that have been unified. And so the idea is now that if you have replaced that block, you can optimize the multiplication. And ideally, if you have two blocks that have been replaced by, I don't know, sometimes my headset seems to shut off. I hope you can hear me again. So you can apply optimized multiplication if you have blocks that were basically replaced by a scalar. And finally, there's another set of methods that makes use of specifics that we see in model architectures. So one is batch norm folding. So batch normalization is something that is very, very commonly used in neural networks nowadays. And so basically you get a mean and then the variance over your batch. And yeah, you try to do scaling using these parameters. So the idea is now you can actually store those batch norm parameters separately and apply them to the weights, and you get a better compressibility of the transformed weights, because you've basically taken out some homogeneous factors of this tensor. And a bit related is local scaling, with the idea that sometimes you may have rows that are at various magnitudes. So you introduce a scaling factor per row and store it separately. If it's used together with batch norm folding, you even don't need no additional parameters, but you can integrate it there. And those factors can be adjusted using fine-tuning. So quantization is actually fairly straightforward. About the first two, I don't think I need to tell you much. You probably know that. So one is just having uniform nearest neighbor quantization, so basically having a fixed quantization scale. The other one is creating a codebook of a tensor. Of course, there's the trade-off that you need to store the codebook somewhere. So it may work for for some tensors may not be so useful for others. And a more interesting thing is what is called dependent scalar quantization or trellis-coded quantization, where the idea is you have two scalar quantizers that have interleaved scales. So you get a better precision, and you have a procedure of switching between them. It's basically a state machine with 8 states, and depending on the values, you can switch to the state and then do the same on the reconstruction side. So this improves the approximation you do with your quantization a bit without much additional overhead. And finally, entropy coding, it's done with a method called deep Kabak, which is an adaptation of the context-adaptive binary arithmetic coding Kabak, which I guess many of you know. It's also widely used in video compression. So it goes through binarization, context modeling steps, and then arithmetic coding of the regular and bypass pins, where some adjustments of the method have been made to better fit the properties of the quantized tensors coming out of the earlier pipeline. So you go through a number of steps with certain flags, and there's separate models for each of these flags, and you choose from a fixed set of models, and then you come to bins that are either regular or bypass bins, and both of them are exponentially Golomb coded numbers. So it's more the logic how it's applied that's adjusted to the tensors. Otherwise, it's fairly similar as the basic Quebec method. So the decoding step is output of and using the encoding tensor and outputting it in some way. It can be integer or floating point, or it can be a block, so a set of combined tensors. So for example, if you had deep composed tensors, you can have a set of tensors that are output together, depending on what the target platform needs to make best use of it. And there's also support for parallel decoding. So you can choose during encoding to specify entry points in tensors, and then you can have parallel decoding of tensors going on. There's also the option that you go layer-wise in the decoding process, which is especially if you have very memory-constrained environments, then it might be useful to only load one layer, do the decoding, do the processing, and then move on to the next layer. So the specification comes with a high-level syntax. As I said before, the idea is not to have another exchange format, but of course some glue is needed to represent the data. So there's a sequence of units that have size, header, and payload, and there is a start unit which just initializes the stream. Then, quite important, there are things called model and layer parameter sets, which basically describe which encoding parameters have been applied to the entire model or a particular layer. There's a place to include a topology using existing topology formats. There's units holding actual data, where the compressed data is actually what is used in this specification, and quantization data is something that has been introduced for compatibility with the quantized representations we already have, for example, in ONNX and NF. And there's also a thing called an aggregated unit for grouping units that should be decoded jointly, and they can be linked together with that aggregated unit. So I already mentioned the existing exchange formats. So there's basically two ways of doing that. Either including topology in the encoded bitstream. So this is supported for ONNX, NF, TensorFlow, and PyTorch. It also supports encoding just some of the tensors. So you could specify that you have now a bitstream that includes some coded tensors, and the other ones would be the raw data as they were. And as I mentioned, there's compatibility with quantization format supported in those formats. And also we have recommendations for doing it the other way around. So for replacing tensors that you find in NF and also ONIX, I should add that to the slide, where you basically replace the native representation they have for their tensors and plug in a compressed data package at this point. And basically there's a few things you specify in the header, and then you could also refer that tensor to an MPEG neural network decoder to reconstruct it. So in terms of the performance, here's some result for the transparent use case. So use case that is with basically no performance loss over the uncompressed model. And you see here the compression ratio. So for VGG16, we get slightly below 3% of the original model size. For ResNet to 6.5%, and for MobileNet to about 12%. DCase is an audio classification model that also gets down to 4%. And then we have what's called UC12B here. That is an encoder model for still images that gets to 17%. That's also why here the metric is a different one. For the other one, it's always the top 1, top 5 accuracy, while here we have PSNR and SSIM as we're doing image compression. So it's similar than the things I've shown for pruning before. With models like VGG16 that are relatively large, you can get down to very small size, while for mobile nets models that are already compact, there is of course less to gain without losing performance. So this is all without performance loss. Of course, if you can afford some performance loss, you could get to even lower sizes. So this is an analysis of the different steps in the model. So basically the white part on the right is something we always achieve, and then you see as we add certain things, we get down to the target performance, and you see that there are some things that make smaller contributions, and then there's for some of the models, for example, decomposition adds quite a bit to the performance. And finally, here's some performance plots of top 1 accuracy. So this is for starting from an original pre-trained model as you would find it on a model zoo, and you always have here the solid curves with what is done with the test model, and there is also to compare the entropy coding, just applying BSIP2 on the output of the other part of the pipeline to see what the difference is in using an adjusted entropy coder. And you also see here that, for example, if you look at the blue VGG curve, you stay still stable around the 3%, slightly below. Then there is a slight drop where we get maybe down to 1.5%, and then you get a steeper drop, and that is roughly the same for all the models. You just see that the plateau on which you just get a slight performance decrease is longer for some models, but then usually there's a point where performance starts to drop very, very quickly. So yeah, you see the overview here for the image and audio classification ones, and also for the image encoder, from which you see that this has a slightly different behavior, and it's more tolerant as you go through the compression ratio. It's only very, very far down the performance breaks down, but otherwise you have a better way to choose a trade-off. And this is just a similar plot with low rank decomposition, which you basically see the whole plot is shifted to lower compression ratios, but also then it drops off more quickly for some of the models. So just quickly on what's ongoing now, we are working on incremental compression. So there's use cases that do not need to send entire models, but updated models. So deploy and update to mobile devices, or things like federated learning, where you send model updates. And the idea is you encode a model with respect to a base model, and supporting both tensor updates with structural changes, like you change the number of output classes of your model, and of course the actual tensor updates. And we have some initial results, and we see that for updates in distributed training, we're getting to well below 1% of the size of the base model for the update without any performance loss. Yeah, so with that I would actually just wrap up. So this is the first standard for compressing neural network parameters. It compresses for most models to less than 10% without performance loss, significantly more for others. It's trying to have interoperability with exchange formats and not getting tied too much into hardware specifics. So the compression standard is now going to its final ballot. The reference software is under development, and the first public release will be made in autumn. And work on incremental compression is ongoing and will probably result in a revision of the standard. So yeah, that's all.
Thank you, Werner, for the nice, interesting and comprehensive talk.